is partial derivatives. Okay. Partial derivative with respect to f, of f, to x variable, okay, where it's f of xy. Maybe I'll put that in here. F of xy. With respect to x, written f sub x of AB, okay, is where we fix y and take the derivative with respect to x only. That is f sub x evaluated at AB is equal to the limit as h goes to 0 of f of a plus h comma b minus f of AB all over h. So that's the partial with respect to x. Okay, f sub x at AB. Okay. Okay. Similarly, the partial derivative with respect to y written f sub y AB is f sub y AB is equal to f sub a comma b plus h. Okay, so we're fixing the x and we're letting the y vary, minus f of AB all over h. Oh, sorry, that's the limit. Forgot my limit. Okay. Okay, so some notation with respect to partial derivatives. Okay, f sub x of xy is the same as f sub x, okay, which is the same as the partial of f over with respect to x. Now this symbol is a Roman d, okay, it's not d. D is df df dx. That's just your first derivative, okay, with respect to x. That's only when we have a single variable, okay. This is where we have multiple variables, and this is a Latin d, which does not look like this d. So that d is not the same as that d. So do not make that mistake there. Okay. So in the notation, okay, this guy is not the same as that guy. So this is partial. This is full. Partial derivative, full derivative. Okay, so keep that in mind. Okay, this can also be written as dx of f of x sub y. Okay, you could also see it as dz dx. Okay, you could also see it as f sub 1 or d1f or dxf. Okay, those all mean the same thing. It's just a lot of different notation meaning the exact same thing. That's your partial on x. Okay, this is your partial on x, and the on just means with respect to. It's just an easier way to say with respect to. Instead of saying with respect to every time, we just say the partial on x. Okay, it's df on x, on dx. Okay, partial of f on x. Okay, with respect to x. Okay, similarly, f sub y of xy is equal to f sub y. The more often than not, you're going to see this notation. Let me use a different color. You're going to see this notation. You're going to see this notation, and you might see this notation. All the other ones you probably won't see. Okay. So f sub y equals the partial of f with respect to y, which is equal to the partial of z with respect to y. Okay, the other ones, I'm not going to even bother writing. You may end up seeing d2f. That just means take your second variable, okay, or f sub 2, or dyf. Okay, so, but again, that's kind of confusing. What's 1, what's 2? So we don't really use these much at all. We won't be using them in this course anyway. Okay. Okay, number 1. Okay, if f of xy is equal to x cubed plus x squared y cubed minus 2y squared, find f sub x of 2, 1 and f sub y of 2, 1. Okay. So think of this as like taking, implicit differentiation, but you're letting one of them be constant. Okay. You're letting one of them be constant, and so you're just allowing the variable that you're not taking the derivative on to act like a constant. So if we took f sub x here, okay, then the x would be what I'm taking the derivative of, which means this y cubed here is a constant. Just treat it like a constant. So this is going to be 3x squared plus 2xy cubed, or we could put the y cubed in front. It doesn't matter, because this is just a constant, which would go with the 2. Okay, minus 0, right? Because the 2y squared would be a constant, and the derivative of that is 0. Okay, so I guess I'll put the minus 0 in there. Okay, so this is equal to 3x squared plus 2xy cubed. Okay, and so that's what f of x is. Well, if I plug in f sub x of 2, 1, then this becomes 3 evaluated at the point 2, 1. Okay, this is going to be 3 times 2 squared plus 2 times 2 times 1 cubed. So this is going to get what? 12 plus 4, which is 16. So that's 16. Okay. Okay, what about f sub y? Okay, f sub y, that's going to be fixing x and allowing y to vary. So that's 0. Derivative of the x value here is 0. Okay, plus x squared times 3y squared. Okay, minus 2 times 2y. Okay, if we clean that up, we're going to get x squared, 3x squared y squared minus 4y. Okay, so we want to evaluate that, f of y at 0.21. So we get 3 times 2 squared times 1 squared minus 2 times, or minus 4 times 1. What the heck's going on here? Did it freeze on me? Please tell me it didn't freeze on me. I think it froze on me. Why it does this, I have no idea. I think it gets too hot is what the problem is. And it just likes to freeze. Okay. Let's try to reboot. Okay. Okay, we're back. See, let's see how long it takes for us to freeze again. So hopefully not. Hopefully a long time. Okay, so we're going to do 4 times 1. So this is going to be 12 minus 4, which is 8. Okay, so this equals 8.
Professor, I have a quick question.
Yeah.
Shouldn't the 3 be next to the y?
The 3 be next to the y.
For the second line from the bottom?
Right? No, because I just pulled it. I pulled it out
Okay.
in front.
Oh, okay, I see.
I just put it in alphabetical order. Okay, so that's equal to 8. Okay, number 2. Okay, if f of xy equals 4 minus x squared minus 2y squared, find and interpret okay, f of x 1, 1 and f of y 1, 1. Okay, what does this mean? Okay. Okay, so we have this function, okay, and we want to find out what's happening at this point for x and y. So let's think about intuitively what's happening here. So let's find the derivative, okay. So f sub x, okay, is going to be equal to negative 2x, okay. F sub y is going to be equal to negative 4y, okay. Allowing the 4 to be a constant goes away, allowing the 2y, negative 2y squared to be a constant if I'm taking derivative with respect to x. Okay, so what does f of x 1, 1 look like? Well, that's just going to be negative 2 times 1, which is negative 2. And what's f of y of 1, 1? Well, that's just negative 4. Okay, so let's think about what this means intuitively. Well, we have this function z equals 4 minus x squared minus 2y squared. Okay, and this is some sort of surface. Okay, so the x's and y's dictate what's happening on z. Okay, so it's some sort of surface. Okay, so at the point 1, when x is 1 and y is 1, well, what's z? Let's calculate the point that we're actually looking at here. Let's calculate the point here. So if x is 1 and y is 1, then what's z going to be? Okay, so z, we'll call this z of 1, 1. Okay, the z value is going to be equal to 4 minus 1 minus 2. Well, that's just 4 minus 3, which is 1. So at the point 1, 1, 1, right, because that would be x, y, and z, which we're calling f of x, y. Okay, at that point 1, 1, 1, where's that point? That point would be 1, 1, 1, right? So we would go out 1, oops, wrong color. We would go out 1 in the x direction. We would go over 1 in the y direction. And we would go up 1 in the z direction. So maybe the point is right here from our perspective, right? But there's a surface, okay? There's a surface here, okay? And so what's the partial derivative with respect to x mean? Well, it means we're fixing y. We're letting y be constant. So that means that the slope of the tangent line that runs through, okay, that runs parallel to the xz plane. Okay, here's the xz plane, right? Okay, so the slope of the tangent line parallel to the xz plane, okay, is this value here. It's negative 2. Okay, so that means that if we think of it like a surface, okay, that means we've got a point on here. That means that if we're running parallel to that xz plane, the slope of the tangent line in the x direction Okay, the slope of the tangent line in the x direction is -2. Well, what does that mean? Maybe it's easier if we draw it as a dome. It'll make more sense. Okay, so let's have this be a little bit less steep. Let's have this be a little bit more steep. Well, other way around. A little less steep and a little more steep. Boom, just like that. Okay, so a little less steep, a little more steep. Okay, and we're going to come out like this as well. Okay. Okay, let's think about this as our surface. Okay. Now, what happens, I'll do this in different colors. What happens when I'm at 1, 1, 1, and I take my tangent line at 1, 1, 1 in the x direction? Well, what's my slope? My slope is -2. That means that every time I move in the x direction, what happens to my z value? Whenever I move 1 in the x direction, I move down 2 in the z direction. I go downhill by 2 units. Does that make sense? But what about the y direction? What about the y direction? If I kind of get rid of this stuff that I put up here. Okay. What about the y direction? Well, the y direction, if I look at the y direction, it's a lot steeper. Whoops. Making it not good.
-4?
Yeah, exactly. It would be -4 in the y direction. Okay, again, we have an axis here. Okay, and so think of it like this, okay? Think of it like this. You're up here on this ridge, right? Think of it as half dome, right? Think of it as half dome. Okay, everybody know what half dome looks like in Yosemite? If Yosemite still exists, anyway, I think it all burnt down, but I think half dome is still there. Okay, so if I'm standing right here at the very peak of half dome, which direction am I not going to want to walk in? Which direction do I not want to walk in? Which direction would be really bad to walk in if I was at the very top of half dome?
Towards the drop.
Yeah, towards the drop, right? Towards the drop. Because the derivative in the x direction would be undefined. Does that make sense? The derivative in the x direction, if I took the with respect to the x-axis, okay, even if it was like this, that would be a really bad move. It's like if I'm standing here and the curve of the mountain is such that I'm going to take one step off and I'm going to drop, that's a very steep slope in the x direction. That's my partial derivative. That's my partial derivative in the x direction. Boom. Okay, really bad. But what if I turned this way? Orthogonal to the x direction. I turn to the y direction. Am I still safe? Am I safe to move in the y direction one step? Yes, I'm safe. Why? Because the slope in the y direction is not undefined. It might be like this. Right? So this would be f sub y, whereas this guy here is f sub x. Does it make sense that the slope in different directions on the surface are going to have different values? Does that make sense? So your partial derivative in the y direction is going to be different than the partial derivative in the x direction. Okay, so intuitively, what does this mean? Well, this means that the slope of the tangent line to the curve f of xy at the point 1, 1, 1, okay, parallel, okay, along the x-axis, basically, parallel, okay, I should say in the direction of the x-axis, not, well, it's not even in the direction, we'll just leave it as parallel. Parallel to the xz plane, okay, because you just want to go in the direction of that the xz plane is going, okay. Okay, I just oriented the point here at the center. This point is not oriented at the center though, so keep that in mind. That you're still going in the x direction, but you're not on the x-axis. Okay, you're parallel to the x-axis. Okay. What's the slope of that tangent line? The slope of the tangent line parallel to the xz plane is -2. It means I'm going down 2. Okay, whereas the slope of the line parallel to the YZ plane has slope of -4. Okay. Okay. Example 3. Okay, find f of sub y, f sub x, f sub y, and f sub z for, okay, f of x, y, z equals e to the xy natural log z. Okay. We can take and find partial of x, partial of y, and partial of z. So df dx, what's that going to be? Df dx, okay, the partial with respect to x, okay, the partial on x is going to be, well, natural log z, that's just a constant. So I'm going to put that on the front. Natural log z, that's a constant. And then I'm going to take the derivative of e to the xy. Well, that's just e to the xy times the derivative of xy, but keeping y as a constant means that the derivative of xy, if y is a constant, is just y. This is times y. Okay, so maybe I'll rewrite that as y natural log z e to the xy. Okay, or maybe I'll write it like this: y e to the xy natural log z, since that's what's in natural log z was last in my original equation. Okay, what about the partial with respect to y? Okay, partial with respect to y. Well, same deal, right? So natural log z e to the xy, but this time it's x that's in front. So x e to the xy natural log z. Okay, and then what's the partial with respect to z? Okay, well, this e to the xy, that's just a constant. And the derivative of natural log z is just 1 over z. So this just becomes e to the xy over z. Okay. That was easy. Okay, let's talk about second partial derivatives. Let's go 2 stages down in our derivative inception here. Okay, we call these second partial derivatives.
Can you scroll back down a little bit?
Yeah, sure. Is that good? Okay, second partial derivatives. okay, or we call these second partials. There, how's that? Better? Okay, is f sub x of x, or we just say that this is f of xx. Okay, or we could say that it's d2f of dx squared. It's another way of writing it. Okay, so, okay, there's f sub x sub y, which means take the partial with respect to x and then the partial with respect to y. Okay, this is f sub xy, partial with respect to x first, and then the partial with respect to y. Okay, this is dx of df dy, which we say is d2f of dx dy. Okay. No, that's backwards. I'm sorry. This is dy dx. Okay. Again, the notation gets a little scary. Okay, it just means, okay, we're taking the, is that right? No, this is right. This is wrong. I'm sorry. This one's wrong. We're taking the derivative with respect to x first and then with respect to y. There we go. Okay, which is dx dy. Partial with respect to x, partial with respect to y. There we go. Okay, so f sub y x means take the partial with respect to y first, and then the partial with respect to x. So d dx, take the partial with respect to y first, which is d2f over dy dx. Okay. Okay. And then f of y is equal to fyy, which just means take the partial with respect to f twice, but take it with respect to y this time twice. Okay, partial y squared. So that's that notation. Okay, what we're going to be using in this class, because it's not very confusing, is this here, the f sub x, f sub xy, because it lends itself to the correct order that you take these partial derivatives in. Okay, number 4 here. Find all second partial derivatives for f sub xy equals x cubed plus x squared y cubed minus 2y squared. Okay. Okay, now this is a polynomial equation, which is kind of nice. Okay. All polynomial equations are continuous, which is really nice, which tells me that if I take partials in any order, I will get the same thing. So it's a nice about continuous functions there. Okay. So this is a nice curve, nice surface. Okay. So let's take our partials here. Let's first take our partial with respect to x and our partial with respect to y. Partial with respect to x, that's 3x squared plus 2xy cubed, right? Okay, I think we already did this one, but it's all good. Okay, and then f sub y, that's going to be 3x squared y squared minus 4y. Okay. Now let's do f sub x with respect to y. Okay, so now fix this partial and then only take the derivative with respect to y. That means that the 3x squared here is a constant. Okay, and so we're just going to be left with 6xy squared. Okay. Okay, and then what is f of y sub x? Let's do that one. F sub y sub x. Okay, that's going to be, take the partial derivative of y with respect to x this time. Okay, that's going to be 6xy squared. Oh, that's kind of interesting. 6xy squared minus 0. Okay, this thing's going to go to 0. Okay. Now, it says all 4 of them. This is not all 4. This is the first partials. This is d dx. This is d dy. We need all of them, which means that we have to take f of xx and f of yy. Okay, make sure that you do this on the exam. Okay, make sure that you give me all 4. Okay, not just 2 of them. Okay, but now let's take the derivative, the partial with respect to x, then with respect to x again. Well, what's that going to be up here? That's going to be 6x plus, okay, with respect to x, that's just going to be 2y cubed. Right? Okay, what about fyy? Okay, fyy, that's going to be, bring down the 2 for the y, fix the x, is going to be 6x squared y minus 4. Okay, so there's all 4 of them. Now what do we notice? We notice that on this line, they're identical. Okay, f of xy and f of yx are identical. Okay, and that's a theorem. Okay, notice that f of xy equals f of yx, which means that we could have take our partials in any order and the order didn't matter. Okay, so this is a theorem called Clairault's theorem. Okay, and it says suppose f is defined in an open region.
What's the name of the theorem again?
Clairault's theorem. It's C-A-L. It's French, so however you want to pronounce that. Okay, I'm not French, so I don't know. Okay, Clairaut's theorem. Okay, suppose f is defined in an open region that contains point AB. If f sub xy and f sub yx are both continuous at AB, then f sub xy equals f sub yx. I should say at the point. F sub xy of AB equals f sub yx of AB. Okay. Okay. Okay, number 5 here, I think. Okay, show that Laplace's equation d squared f over dx squared plus d squared f over dy squared equals 0 is satisfied for f of xy equals e to the y, or sorry, e to the x sine y. Okay. So we want to say, well, what's the second derivative, the second partial derivative with respect to x? So that's f sub xx. So the first thing I need to do is find out, well, what's f sub x first? Okay, so take the derivative with respect to x. That's just going to be the same thing. That's e to the x sine y. Okay, take the derivative with respect to y. Well, this becomes e to the x cosine y, right? Okay, what's f of xx? Well, take the derivative with respect to x again, same thing. Okay, what's the derivative with respect to y? Take the derivative with respect to y here, we get negative e to the x sine y. And what do we notice? We notice that this guy is the opposite of that one. So e to the x sine y plus negative e to the x sine y is equal to 0, and 0 is equal to 0, so it checks. Okay, so it satisfies that differential equation. We call this a partial differential equation. Okay. Okay, let's move into 14.4. Okay, our tangent planes and linear approximations. Tangent planes and linear approximations. Okay. Okay, suppose f has continuous partial derivatives period. An equation of the tangent plane, okay, to the surface okay, z equals f of xy, okay, at a point P, we'll call it P naught, which is x naught, y naught, z naught, is, okay, z minus z naught is equal to the partial with respect to x, evaluated at x naught, y naught, that's the slope at that point, okay, times x minus x naught, okay, plus f sub y, evaluated at x naught, y naught, times y minus y naught. Okay, so this is very reminiscent to the point slope form. Think point slope form of a line. Okay, this is analogous to that, right? Okay, so you think point slope form of a line. Okay, well that had just one slope, and then y minus right? Y minus y1 equals m times x minus x1. So this was 2 dimensions. And so the analogy is to move it up to 3 dimensions, where we have z as our f of xy, right? So z equals f of xy. And so before we said, well, this is the slope, right? The slope of the tangent line. If the slope came from a derivative, right? If this is f prime of x, right? F prime of x1, I guess we could say. Right? So f prime of x1 times x minus x1, this is the slope of the tangent line. This is the equation of the tangent line. So this is the equation of what we call the tangent plane. Okay, so if we have a surface, think of it like a bended sheet of metal, and we had a point here, we could have a plane that's tangential to this. Okay, and then we know that the slope of this tangent plane has actually two slopes, right? There's a slope in the x direction, and there's a slope in the y direction. There's an f sub x and an f sub y. Okay, so how does z change with respect to x, and how does z change with respect to y? That will give me the total change of the surface, or the slope of this plane, we could say. Okay, because we're changing 2 dimensions. Okay, every time I take a step on this surface, what am I doing? If I take a step from here to here, what did I just do? Well, I went over a certain amount, but I went over in the x direction, but I also went over in the y direction. So, okay, so there's a net change in both dimensions. Okay. Probably should have my point somewhere else. Whoops. Not parallel to the x-axis. So let's say that the 2 points were right here and right here, right? So in the x-axis, I would have had a net change, and in the y-axis, I would have had a net change. Well, again, it's hard to draw, but you get the idea. I'm not going to spend a lot of time on it, but again, if I were to move from point to point, I would have a net change in the x direction, and I'd have a net change in the y direction. Okay. And so that's the slope of the tangent plane. Okay. Okay, using the partial derivatives. Okay, find the equation of the tangent plane to the elliptic paraboloid z equals 2x squared plus y squared at the point. If I plug in 1 and 1 for x, okay, one second. Okay, so let's find the equation of that. So what do we have to do? We have to do the f sub x, okay, is going to be equal to 4x. F sub y equals to 2y. Okay, so at this point, when x is equal to 1, okay, f sub x at 1, 1 is equal to 4, and f sub y at 1, 1 is equal to 2. Okay, so what's the equation of the tangent plane? Well, this is going to be z minus z naught, which is 3 at that point, 3, is equal to f sub x, which is 4, times x minus x naught, which is 1, plus 2 times y minus 1. Okay, and if I wanted to clean that up, I could solve for z, just like we would put it in slope-intercept form. We could put this in, you know, a plane, you know, with it z equals just x and y. We could clean it up. Okay, z minus 3 is equal to 4x minus 4 plus 2y minus 2. Okay, so if I add 3, we get 1, negative 3. So this is going to be z equals 4x plus 2y minus 3, right? Okay, and that's my tangent plane. Okay, it's my tangent plane through 1, 1, 3. Okay. Okay. If I rewrite this, okay, if I say that z minus z naught is equal to f sub x of x minus x naught plus f sub y of y minus y naught, and I let z naught be f of AB. It's basically when at point AB. So we would say that this is A, B, and F of AB, right? AB, F of AB. That's what we would say. The point at that point. Okay. Okay. So this is Z minus F of AB is equal to F sub X evaluated at AB times X minus A plus F sub Y evaluated at AB times Y minus B. Okay. Okay, and so we could add this guy to both sides. We would say z equals, okay, z equals f sub x a b times x minus a plus f of y a b. We're just generalizing what we did before. Times y minus b plus f of a b. Okay. Actually, I'm going to put that in front, the f of a b. I'm going to put that in front. I'm just going to move it right in front here. Okay, so think of that as your z-intercept. Okay, this is kind of like your z-intercept, right? Because when A is 0 and when B is 0, then we get this f of AB. Okay, that's kind of like your z-intercept. It's going to be where it crosses the z-axis. Okay, what we say is that this thing, okay, if we were to generalize this, okay, that z is really L of x, y, that this is a function now, this tangent plane function. So we have a tangent plane function that we're going to call L of x sub y. Okay, is equal to f of AB plus f sub x of x minus a plus f sub y of y minus b. Okay, to abbreviate it, okay, is called the linearization of f of xy at AB. Okay, so we've made it a linear graph in the fact that the trajectory is along the tangent plane now instead of the original function. So this is an approximation to the original function near AB. It's a good approximation. Near AB. Okay, so and this should be reminiscent of linear approximation that we did in Calc 1. If you don't remember linear approximation in Calc 1, go back and review those notes. Okay, from 2 semesters ago, where we said, oh, you know, we have this curve, and then we have the derivative, and when we're close to this value of x, okay, we'll call it a. When we're close to a, then this linearization approximates f of a. Okay, for values that are really close to a. The further I get from a, the worse and worse the approximation gets. Does that make sense? Okay, so that was linearization in Calc 1. Now we're just doing linearization in 2 variables in Calc 3. Oh, okay, okay, so the linearization okay, also called, or the linear, I'll say linear approximation, also called the tangent plane approximation, tangent plane approximation. Okay, of f of x, y, okay, is approximately, okay, it's approximately this thing, okay, f of AB plus f sub x of x minus a, okay, plus f sub y of y minus b. Okay, and this is all evaluated at AB. Okay, so this is an approximation of the original function. Okay, it's a tangent plane approximation for values that are close to AB. Okay, it's a good approximation for values near AB. I should say comma FAB, because this is a 3-dimensional region. Okay, it's a good approximation near AB, f of AB. Okay. Okay, if z equals 1 second. I'll be right back. Go get yourself a cup of water. My dogs are going crazy for some reason. 1 second. Just want to mute. There we go. Okay, sorry about that. That's the air conditioner repair guy is here. So trying to teach calculus with no air conditioning. It's fun times. Good times. Okay, let's move on. Let's finish this up here. Okay, if z equals f of xy, then, then f is differentiable at AB if delta z can be expressed in this form. Okay, delta z is just the change in z, right? The change in z, which kind of makes sense. The change in z is going to be with respect to a linear drop, okay, linear approximation. Okay, this is not the same as delta z. This is not equal to dz, which is not equal to the partial on z. Okay, partial with respect to z they're not the same. Okay, they're all different. Okay, they mean different things. Okay. Okay, so delta z is a linear approximation. Kind of think of it as slope, right? Rise over run. That's delta z. But the delta z is in two different dimensions. It's delta x and delta y, which we'll get to that. Okay. Okay. If delta z is differentiable at AB, if delta z can be expressed, okay, can be expressed in the form, okay, delta z equals f sub x evaluated at AB, delta x, right? That's that change in x, okay, plus f sub y evaluated at AB of delta y. It's a change in y. Okay. Plus, okay, kind of run out of room here, but I'll continue. Plus some sort of epsilon 1 delta x plus epsilon 2 delta y. Okay, so with some extra nudges, okay, where, whoops, I don't know what happened there. Stop, there we go. Okay, where epsilon 1 and epsilon 2 go to 0 as delta x, delta y go to 0, 0. Okay, so if the change goes to 0, 0, then these epsilons are negligible, okay, as they get closer and closer. So again, it's a proof with respect to the analogy of linear approximation. This is just linear approximation in two variables, multivariable linear approximation. Okay, so let's see how this works in real life. Okay. Okay, what were we on? Example 2. Let's do example 2 here. Okay, find the linearization of f of xy equals x e to the xy at at 1, 0 and use it to approximate f of 1.1 negative 0.1. Okay, so interesting. Okay, so we know that A is equal to 1 and B is equal to 0. Okay, A is equal to 1 and B. So we want to do the linearization of this thing. Okay, so remember L of xy is equal to f of AB, okay, plus f sub x of AB times x minus x naught, plus f sub y evaluated at AB of x minus, this should be A, sorry. This is A and this is B times y minus B, okay. Okay, so let's just evaluate this, see what we get. Okay, first we got to figure out, well, what's our partials, okay? What's the partial derivative of this thing with respect to x? Well, that's going to be a product rule, okay? The derivative with respect to x of x is 1 times the second, the derivative of the first times the second, plus the derivative of the second, that's just going to be y e to the xy. So this is going to be, derivative of the second is y e to the xy times the first, which is x. So this equals e to the xy plus xy e to the xy. Okay, I could factor out an e to the xy if I really wanted to. Okay, I don't really have to, but e to the xy times 1 plus xy. Okay, so that's f sub x. Okay, what's f sub y? Well, hopefully that one's a little easier. Treat x as a constant. Yeah, that's a lot easier. And we get x times x e to the xy, which is just x squared e to the xy. Okay, so that's a lot nicer. Okay, so we want to know, okay, okay, what is L of xy then? L of xy, this is the equation of the tangent plane at 1, 0. Okay, 1, 0, well, 1, 0 what? 1, 0, and then what's f of AB? F of AB, well, what's the original function? If I plug in 1 times e to the 0, that's just 1, so this would be 1, right? So that would be the 0.011. Okay, we want to know, okay, what's the, so this is 1, okay, for f of AB. Okay, plus, let's plug in and evaluate these guys for 0 and 1. Okay, so if I plug in for 0 and 1 here, for f sub x, okay, so let me write it like this. F sub x of, sorry, 1, 0, okay, times x minus 1, plus f sub y evaluated at 1, 0, times y minus 0. Okay, so what is this guy going to be? Well, plug in 1 and 0. Okay, well, this is going to be e to the 1 times 0 times 1 plus 0 times 1. Well, that whole thing goes to 1. This goes to 1, and this goes to 0, so the whole thing goes to 1. So this just becomes 1 plus x minus 1 plus, okay. And what is this thing going to become? F sub y. Okay, well that at 1, 0, this thing goes to 1, and this thing goes to 0. Is that right? No, that goes to 1, I'm sorry. This goes to 1 as well. Okay. So this is plus 1 times y minus 0, which is y. Okay, so this is equal to 1 plus x minus 1. The 1s are going to cancel out, and I'm just left with x plus y. Okay, is equal to x plus y. Okay, so how is this going to help me? I want to get a linear approximation of f of, okay, f of 1.1, negative 0.1. So we're only 1/10 away from where we started, right? We're only 1/10 away in each direction, in the x direction and in the y direction. Okay, we're only 1/10 of a unit away in each of these. Actually, it's the other direction because y is negative. Okay, so 0.1 in each of those directions. Okay, and so the linear approximation here is really easy to get, right? It's just x plus y. So we would say that f of 1.1 negative 0.1 is approximately equal to 1.1 plus negative 0.1, which is equal to 1. So the function is evaluated. We can just add the x's and the y together if we're really close. We just add the x's and y's together and we get an approximate value for the function. Okay, as we move further and further away. Okay, let's compare this to the actual value of the function. Okay, so again, you got to think in terms of a surface here. And we have our tangent plane, right? We have our tangent plane, and we're moving a little bit in each direction, which would be about right here. We're moving from this point over to this point, and we're saying instead of doing it on the surface, we're going to do it on the plane, the tangent plane, which is a lot easier to calculate. Okay, because it's essentially the same thing when we're really close. And so it's what's called a linear approximation. So let's compare this to the actual result. Well, what would be f of 1.1 negative 0.1? Let's plug that into our original function. X e to the xy. So this is x e to the xy. Okay, and if I plug that into a calculator, I get this to be approximately 0.98542, okay, which is really close to our approximation. Okay, and the reason they did this is this was before the advent of the personal computer. Okay, the word computer actually comes from the idea that that was a job. Somebody who computes is a computer. Okay, computers before 1960s was a person. So if people wanted to go to the moon, okay, they had to have people who were called computers compute all these values by hand. They were all done by hand. So they were like, oh, well, it's easier to compute this approximation than it is to compute the actual value all by hand. And when we're really close, it's a good approximation. Okay. Now we have computers to do all that for us. Okay, computers the machine, not the computers the job. Okay, it'd be like, what do you do for work? Oh, I'm an investor. Oh, what do you do for work? Oh, I'm a computer. 100 years later, people would be looking at you and be like, you think you're a computer? What the hell is wrong with you? They're like, well, that was a job, okay, in the early 19th century. But now it just took, that machine took the place of that job, someone who computes. Okay, differentials. Okay, in 2 dimensions, if we think back to Calc 1, in 2 dimensions, dy is equal to f prime of x dx. Okay, and we would say that delta y, the change in y, okay, is approximately equal to f prime of x times the change in x. Okay, so this is the slope, right? The slope, okay, the change in y for a linear approximation over the change in x is approximately the slope of the tangent line, okay? So at that value, okay? And this works for small delta y and small delta x, okay? They have to be small, otherwise, again, all bets are off. Okay, you get way out here. Yeah, it's not a good approximation anymore. You get close, it's a good approximation. Okay, in 3 dimensions, okay, in 3 dims, okay, dz is equal to f of x of xy dx plus f sub y of xy dy. Okay, dz is equal to the partial of z with respect to x dx. This is a d, not a partial. Okay, this is a dx. dx. Okay, this is a partial derivative. This is a partial. This is not a partial. Okay, this is a first derivative. Well, it's a differential. It's called a differential. It's the differential on x. Okay, this is a partial on x. That's the differential on x. Okay, differential on x, partial on x. Try to not get them confused. Okay, plus the partial with respect to y, dy. Okay. Okay, so and delta z, okay, the change in z, okay, is equal to the function evaluated for x2, y2 minus the function evaluated for x1, y1. Okay, so we take these functions and that's the change in z. Okay. Okay, so let's find some differentials here. Okay. Okay. So number 4 here. A. If z is equal to x squared plus 3xy minus y squared, find dz. Okay. Okay, find dz. Okay, well, we just need to find our partials. Okay, so partial of z with respect to x is going to be what? Well, that's 2x plus 3y, right? And then the partial of z with respect to y is going to be equal to 3y minus 2x. Or sorry, 3x minus 2y. Okay, yeah. Okay, and so they're saying that dz, okay, the partial, the differential with respect to z, okay, the differential with respect to z is equal to the partial of x dx plus the partial on y dy. Okay, so that's the partial, that is the differential of z. Okay, that's the differential of z. Okay, B. If x changes from 2 to 2.05 and y changes from 3 to 2.96, find dz and delta z. Okay, so find dz and delta z, and then compare the two. Okay, so what's dz going to be? Okay, dz, well, we just calculated that out. dz is equal to, okay, 2x, okay, so 2x, so 2 times, think of this as xy, as 2, 3, right? And then we're changing from 2, 3, we're going to 2.05, 2.96, okay. So, okay, so the differential with respect to z, okay, the differential with respect to z, okay, is going to be 2 times 2 for x plus 3 times 3 for y times the change in x. Well, what's the change in x here? The change in x is 0.05. Okay, plus, what's the change in, what's y? Well, that's, what's the partial derivative on y? Well, it's 3 times x. We're going to let that be our starting point. 3 times 2 minus 2 times 3. Well, that's kind of nice, because that whole thing just goes to 0, right? Okay, times what's the change in y? Well, that's negative 0.04, but it really didn't matter because, oops, damn it. Lost it again. I was warned though too. That's the bad part. Is this time I was warned. This time it was my battery that went. I apologize for the stuff that's going on today with my computer. I got to eventually send this thing back, but I'm hesitant to send it back because then I have to go like a week without it, and I'm like, well, what the hell am I going to do then? So in the meantime, I kind of just put up with it. Okay. Oh, okay, perfect. Okay. So this thing goes to 0, which is nice. So dz is equal to, what is this? 9 and 2 and 4 is 13 times 0.05. So the change in z is 0.65. Okay, so that's the change in z there, 0.65. Now what, this was easier, the reason we do this is because this was easier to calculate than possibly what delta z would be. And delta z, again, is f of x2, y2 minus f of x1, y1. Okay, so what was the original function? The original function was, okay, z equaling x squared plus 3xy minus y squared. And if I want to plug in, okay, if I want to find out, well, what's f of, what was it, 2, 3, f of 2, 3, I would have to go, okay, 2 squared plus 3 times 2 times 3 minus 3 squared, which might not be such a problem because that comes out to be 13. Okay, but if I try the other one here of f of, what is this, 2.05 and 2.96, that one's a little bit tougher. We could plug that in a calculator though. So 2.05 squared plus 3 times 2.05 times 2.96 minus 2.96 squared, which comes out to be 13.6449. Okay, so if I take, this is my second point, this is my first point. If I subtract those, what do I get for delta Z? I get 0.6449, which is, it's close to 0.65. Okay, okay, there's some error there. There was some error. Okay, but it was a little easier to calculate. Okay. So we want, the idea is that we want delta Z, but we will accept dz. Okay, and we can get dz based on a partial derivative. That's the idea here. Is sometimes when if we take the partials of these things, we can make them easy to work with. Okay. Okay, let's see how this works in real life here. Okay, so number 4, example 4. Okay, the base radius and height of a right circular cone are measured as 10 centimeters and 25 centimeters respectively. And have a maximum error of 0.1 centimeters for each. Okay, use differentials, can't spell, differentials to calculate the maximum error of the volume. Okay, so we want, we want delta V, but we'll accept dV. Okay, so what's V? V is equal to, okay, for this cone, we're going to make it a right circular cone. Okay, right angle with R and H. Say what?
Can you scroll down just a little bit?
Sure.
Thank you.
Okay, so what's the volume of a cone? Well, the volume of a cone is 1/3 pi r squared h. Okay. And so we want to know what dV is. Well, dV is going to be dV dr. Okay. Times dr plus dV dH times dH. Okay. Okay. So what's the partial derivative of the volume with respect to r? Okay, so take the derivative with respect to r. I'm going to get 2 pi h r over 3, something like that. Okay, and then okay, evaluate this for r and h. Well, what is r and h? Well, we said that the radius was what, 10? Right, so the radius is 10, so this is 2 pi times 25 times 10 over 3. Okay, so this is what, 500 pi over 3? Okay, that's kind of cool. Okay. Okay, so what's dV dH? Let's take that one. Okay, now take the derivative with respect to h. Well, everything goes away. Everything stays except for the h. Left with 1/3 pi r squared. Okay, so this is just going to be 10 times 10, which is 100. So this is 100 pi over 3. Okay, that's kind of cool. Okay, and so, but what was dr and dh? What was the change in r and the change in h? Well, we said that each of those was 0.1. So the total change in the volume, the maximum change in the volume has to be 500 pi over 3 times 0.1, or 1/10. Maybe I'll write it as 1/10. I'll write it as 0.1, otherwise you're not going to know what I did. Okay, plus 100 pi over 3 times 0.1. Okay, so this is 50 pi over 3 plus 10 pi over 3, which is 60 pi over 3, which is 20 pi. Okay, so dV is 20 pi, which is approximately 63 cubic centimeters. Okay, that's the approximate change in volume, the maximum error. This is the max error. Okay, for that volume, the volume of that cone. Okay. Okay, I'm going to stop there because it is hot as hell in my room, and I'll go talk to the air conditioning repair person and see if they can't cool my place down. Okay, I will see you guys on Monday. Okay.
Thank you, Professor.
Yeah, you're welcome. Thank you.
Bye. Thank you.
Bye.